Above all, I'd like to thank Department of Physics, Namchi Government College and Sikkim University for providing me this opportunity to do project on the topic Pauli's exclusion principle, which was provided by our teacher Dr. C.P. Khatiora for the partial fulfillment of BSc third semester June to December 2020. This video carries 25 marks or sessional B examination. My name is Anup Chetri, my roll number is 19NS0073 and my topic is Pauli's exclusion principle. My contents for the video are introduction to cells, subcells and quantum numbers, Pauli's exclusion principle and then its uses. Before understanding the Pauli's exclusion principle, first we need to understand what are cells, subcells and quantum numbers. We all know that in an atom, electrons surround the nucleus in fixed paths called orbits or shells. Cells are energy levels around the nucleus of an atom. These are also called orbits and they are subdivided into sub-energy levels called orbitals or subcells. Each cell are designated with number n equals to 1, 2, 3 and named as K, L, M, N respectively. As shown in figure here, these are the cells and the orbitals. These are the orbitals. And orbitals are named as S, P, D, F and so on with numeric values 0, 1, 2 and 3. Every orbit has fixed number of orbitals and each orbital has fixed capacity to hold an electron. That means each orbit can only hold a certain number of orbital and an orbital can only hold a certain number of electrons. And next is quantum numbers. Quantum numbers are the set of numbers that describe the position and energy of the electron in an atom. Which means quantum numbers define the position and energy of an electron in an atom. There are 4 quantum numbers, which are first is principal quantum number, which is denoted by n. Principal quantum number designate the principal electron shell of an atom. That is, the value of principal quantum number gives the number of shells or orbits in the atom. Next is azimuthal or orbital angular momentum quantum number, which is denoted by L. The value of azimuthal orbital quantum number gives the type of subcell in which the electron is placed. For example, if value of L is equal to 0, then the orbital will be S. If value of L is 1, then the orbital will be P and so on. Next is magnetic quantum number, which is denoted by ML. Magnetic quantum number determines the total number of orbitals a subcell can hold and its orientation. That is, magnetic quantum number values gives the total number of orbitals in a shell and then its orientation. Next is electron spin quantum number, which is denoted by the symbol ms, and its value gives the direction in which the electrons are spinning. That which means electron spin quantum numbers gives the direction of spinning of electrons in an atom. The values, the possible value range of these quantum numbers are given in this table. The value of principal quantum number n ranges from 1, 2, 3, 4 and so on. Azimuthal or magnetic orbital angular momentum quantum numbers value ranges from 0 to n-1, and magnetic quantum numbers value ranges from -L to L, and whereas spin quantum number only has 2 values, which is +½ and -½ Now the Pauli's exclusion principle. In 1925, the Austrian physicist Wolfgang Wolfgang Pauli proposed his exclusion principle, which he stated as no two electrons in an atom can have the same set of four quantum numbers. In other words, we can state that no two electron in an atom can exist in the same quantum state. Further, it means that if two electrons in an atom have the same value of principal quantum number, orbital quantum number, and magnetic quantum number, then its spin will be either plus half or minus half. Um, the state of an electron can be defined by this group of four quantum numbers. Next is obtaining the maximum number of electrons in a shell and subshell using the Pauli's exclusion principle. We know that for shells K, L, and M, value of n equals to 1, 2, 3, which was depicted in the figure earlier. And since we know that the value of L ranges from 0 to n minus 1, so for K shell, value of L will be equal to for K shell, value of L will be equal to n minus 1, which is for here n is 1 minus 1, which is equals to 0. So value of L for K shell will be 0. For L shell, value of orbital quantum number will be 2 minus 1, which is 1. So its value will range from 0 to 1. 0, 1. And then for M shell, the orbital quantum number will range from 0 to 3 minus 1, which is 2. So it will be 0, 1 and 2. 0, 1, 2. And for next, so here the shells will be S shell, S subshell or orbital. This will be P orbital, this will be S orbital, this will be P orbital, this will be D orbital. This will be D orbital. And then value of ML. It ranges from minus L to plus L. So here minus 0 to plus 0 will be 0. Here also it will be 0. For here minus 1 to minus 1, 2, minus 1, 0 and 1. Minus 1, 0, 1. Here the value of magnetic quantum number will be 0. Here it will be minus 1, 0, 1. Here it will be minus 2, minus 1, 0, 1 and 2. As the value of magnetic quantum number ranges from minus L to L. So minus 2, minus 1, 0, 1 and 2. So the value of magnetic spin quantum number, that is ms, here it will be up spin, down spin, that is plus half or minus half, up spin or down spin, up spin or down spin, up spin, down spin, up spin, down spin. here. From here we can state that s orbital can contain 2 electrons. P can contain 6 electrons, 1 2 3 4 5 6 electrons, and D can contain 1 2 3 4 5 6 7 8 9 10 electrons. After formulating the exclusion principle, Pauli stated that the maximum number of orbitals, maximum number of electrons an orbital can hold can be given by the formula 2l plus 1. So, for s orbital, the value of L will be 0. Therefore, so maximum number of electrons in s orbital will be 2 into 0 plus 1, which will be 2. And for p orbital, value of L equals to 1. So maximum number of electron in p orbital will be 2 into 1 plus 1, which is equals to 2 into 2 plus 1, which is equals to 6 electrons. And for d orbital, value of L is 2. Then using formula we get 2 into 2 plus 1, which is equals to 2 into 5, which is equals to 10 electrons. So from this above table we can state that Pauli's formula for finding the maximum number of electrons in an orbital is correct, which is 2 into L plus 1. And after determining the maximum number of electrons present in an orbital, we can use this formula to find the maximum number of electrons in a shell. For that, we know that value of L ranges from 0 to n minus 1. So we can use this formula 2l plus 1 to find the maximum number of electrons in a shell. For that, we need to sum all of the possible values of n. Limit L equals to 0, n minus 1, 2l plus 1. So we can write this as 2 summation L equals to 0, n minus 1, 2l plus 1. We can further solving this, we get 2 first value starts from 0, that is 2 into 0 is 0 plus 1 1, which will be plus, then if value of L is 1, then you need 2 plus 1 3 plus which will be last value of L is n minus 1. So 2 into n minus 1 plus 1, 2n minus 2 plus 1, which will be 2n minus 1. So 2n minus 1. Here this forms an AP. Because here if the value of L is 2, then it will be 5. So as we can see, this forms an AP, so we can say that its total sum, we know that in an AP the total sum can be given by n by 2, which is number of terms by 2 into first term plus last term. Since we have both first term and last term, we can write this as 2 n by 2. A is 1 plus 2n minus 1. 2 gets cancelled, plus 1 minus 1 gets cancelled, which will be equal now, which will be equals to 2n square. This is the formula for the maximum number of electrons in a shell. Next is how Pauli's exclusion principle helped in classification of elements. We know that the ground state of an atom is that state in which electrons of an atom are in the lowest energy state possible. Hence, lowest energy orbits. Hence, knowing the number of electrons in the ground state, we can find its electronic configuration. For example, ground state configuration of beryllium with atomic number 2 is 1s2 2s2, and for magnesium atomic number 12 is 1s2 2s2 2p6 and 3s2, and for calcium is atomic number 20. Calcium is 1s2 2s2 2p6 3s2 3p6 4s2. In above all of these examples, we get that they possess 2 electrons in their outermost orbital. Hence, these elements show same chemical properties, and physical properties like density, etc. This shows that after certain period of atomic number, we come across atom with similar properties. This above example shows that after a period of atomic number, we come across the atoms with same chemical and physical properties. This justifies the classification of elements on the basis of electronic configuration.